Hello to all my dear learners. I am Aishwarya Sharma, welcoming you all on the platform Gate Wallah. Friends, today the task is Shear, and I think it is the fifth session of one short series, and today we will be completing Shear. So let's quickly see what are the agendas today. So we are going to see shear stress profile. After that, we will be seeing what all are the effects of shear, especially in terms of crack. Then we will be seeing strength versus stress, action versus reaction. Then we will be seeing how to approach for our shear design, how to go for stirrups, when to go for vertical stirrups, when we can take advantage of bent up bars and all. And eventually we will be completing the session with a numerical. Okay, only one numerical will be there today, but important one. Okay, so let's start the session, my dear friend. So first topic is shear stress profile. Okay, so in shear stress profile we can see in homogeneous beam, if we are talking about strength of material, my dear friend. So in strength of material you must have plotted this shear stress profile. This shear stress profile is parabolic in nature. If I am talking about the exact equation of shear stress, so this Q is equal to V over IB into AY bar. Okay, where V is the shear force at this section, and I is the moment of inertia of this section about neutral axis, and B is the width of the location where shear stress is to be obtained, and in rectangular beam it is going to be B only. A is the area of the cross section, and area into A into Y bar is the moment of area of cross section, which is actually bounded between the point of consideration and the neutral axis. Okay, because you are going to take its moment of sorry, let me explain you like this. See, this is, let's suppose, point of consideration, and it is located at a distance y, so this is B. So what about area into y bar? What about this A into y bar? So this A into y bar is either the moment of this shaded area about the neutral axis. Okay, so this would be the, let's suppose, y bar, or it is the moment of the remaining unshaded area about the neutral axis. So normally whatever is closer, or whatever is closer to the extreme end, because that captured area would be small, so that we generally consider. If you are talking in terms of mathematics, then it is same. So in this moment, this area moment about this axis is as similar as overall area moment about this axis, because you can see this and this are going to cancel each other. So whatever amount of area is left here, same amount of area is also lying there, and equivalent CG and equivalent CG would have been here same. Are you getting it or not? So if you are going to put all these values, then the nature of graph which you are going to get is parabolic. Okay, let's see, my dear friend. If this is D, if this is D, this is B, and if this is D, so this is D by 2. Okay, what about y bar? Y bar is equal to, y bar is equal to how much? It is y plus D by 2, average of y plus D by 2 divided by 2. Okay, what is the area? Area is B into D by 2 minus y. This is the area, shaded area. So now if we are going to put all these things here, so what is the actual shear stress variation in homogeneous beam? The actual shear stress variation in homogeneous beam is V over BD cube by 12, moment of inertia, into B. Here the B is the width of the section where shear stress is to be obtained, and luckily in rectangular beam that width is constant, multiplied by A. What about area? Area is B into D by 2 minus y. And what about y bar? It is D by 2 plus y, average of that. So finally whatever you are going to get here. So actual shear stress at a location y from neutral axis is given by B, and B will cancel here, 2 and 6. So it is 6V upon BD cube. A minus B, A plus B is A square minus B square. So you can see that this is the actual shear stress profile, and the nature of this curve is going to be parabolic because y is having the highest degree as 2. Okay, so you can see when y is equal to 0, at that point of time this function is maximum, because the maximum value of this bracket will be at y is equal to 0, and whatever is the value of y, doesn't matter whether it is positive or negative, so it is going to reduce this bracket. So ultimately you can see that this value is going to be equal to 0 when y would be at d by 2. Means when my point of consideration would be extreme top point or extreme bottom point, at that point of time q is equal to 0. Okay, so let me plot this graph now. Okay, so at y is equal to 0, q is maximum. It is 3 by 2 of average shear, and here it is going to be 0. Okay, so this is the case here. This is the case. Okay, and this value is okay, and this is parabolic in nature. Parabolic in nature. And one more thing, although this maximum value is V over BD is what? It is average shear stress. Shear force upon total area is average shear stress, and 3 by 2 of BD is 1.5 times of average shear stress. Had this been a case of circular beam, in that case instead of this 3 by 2, 4 by 3 would have come. But all such things are the part of your strength of material, so you must be watching it there. Okay, so what are the shear stress profile for I section, for T section, for circular section, for triangular section. Okay, but in RCC we will be only reading this rectangular segment. Are you getting it or not? Now my dear friend, let's see that what is the shear stress profile in RCC beam. Please try to understand one thing, that RCC beam is not your homogeneous beam. Okay, if I am even considering concrete to be homogeneous, still it is not as symmetrical as your steel or any other material homogeneous beam. You know why? Because you know here concrete is effective, continuity is maintained of the material from a strength point of view only till the neutral axis. But the moment you are going to be in tension zone, so their concrete is becoming ineffective. Okay, so what is happening here? So till in compression zone, if this is B, let's suppose if this is let's say XU, so till compression zone, okay, so graph is parabolic, it is increasing. So at neutral axis this value is maximum. I hope it is visible. Yes, at neutral axis this value is maximum, and since the moment you are going down of this neutral axis, you can see that there is no concrete. If we are going to calculate the value of A into Y bar here and A into Y bar here, so captured area is going to be equal to this much only, because even if you are calculating at this level, still you can say A into Y bar is shaded area only. Are you getting it or not? Because in this zone concrete is not effective, so the value of A into Y bar is not going to be changed. And you see here that V is same, I is same, B is same, area into Y bar, this is the only factor due to which your actual stress distribution is taking place. So when you are going when you are going down, my dear friend, when you are going down, so doesn't matter whether you are calculating A into Y bar here, 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 the only component of effective concrete is there on the compression side. Are you getting it or not? Okay. So that is the reason why the shear stress is becoming constant at the moment you are crossing your neutral axis. And one more thing, this constant value is only considered till the CG of the reinforcement, till the CG of the tensile reinforcement. Okay, so beyond CG of the tensile reinforcement, we will not be considering the graph. So many times in questions they have asked, what is the actual shear stress profile in RCC beam? Okay, then answer is graph is parabolic till neutral axis. After that, it is becoming constant till CG of the tensile reinforcement, isn't it? Okay. Now, no doubt this graph is increasing here and then it is becoming constant. So, what is the value of this stress? We haven't calculated this value. So, what is the maximum value? We are knowing the maximum value in the case of homogeneous beam, that is 3 by 2 times of the average shear stress. But here, my dear friend, what is the maximum value? So, how you are going to get that? So, maximum value you can calculate at the neutral axis or anywhere between the neutral axis and CG of the tensile reinforcement. That is for sure. Okay, that you can calculate maximum value anywhere between the neutral axis and CG of the tensile reinforcement. Okay. So, just to understand that what we did, we are simply considering the section of this beam, that for example, you know that this is a simply supported beam which is loaded with a UDL, and this is the shear stress, shear force profile of this beam, and this is the bending stress profile of this beam. Bending moment is maximum at the center and shear force is 0 at the center. Shear forces are maximum at the ends and bending moment is 0 at the ends. Nature of shear force is linear. Nature of bending moment is parabolic. Okay. So don't confuse here. Shear stress variation is parabolic, but shear force diagram is linear. Like similarly in elastic theory, bending moment diagram for this particular case is parabolic, but bending stress diagram is linear. Okay. So yes. So here you can see, if you are considering any section between, let me take here section 1 and let me take here section 2. They are differentiated by a very small distance, and that distance is known as dx. That distance is known as dx. Okay. What we are trying to calculate? We are trying to get the maximum value. Okay. Which maximum value? This maximum value. Okay. So this is 1 and 2. Okay. So if I am going to make this 1 and 2 section here, maybe somewhere here. And here somewhere is the steel. Okay. So let's suppose here somewhere compressive forces are acting. C plus DC, T plus DC, dt, and let's suppose if here it is M, so it is M plus dx. If dx would have been 0, in that case C, T, M would have been same. Okay, but this time we are considering these two different sections at a very minute distance dx. So variation may also be little. So what can I write here? That B plus M plus dm is T plus dt into, what is this, lever arm? Lever arm I am writing simply JD. You know the lever arm. Lever arm is D minus 0.42 XU. Okay, or simply I am writing JD, and M is basically TJD. So if you are subtracting second equation from first, then dm you are going to get as how much? Dm you are going to get as dt jd. So dear friends, you know this is the dt and this dt is dm over jd, no doubt it is dm over jd. This dt is dm over jd. And this dt is responsible for shear between neutral axis and the CG of the tensile reinforcement, because you can check it out between CG of the tensile reinforcement and neutral axis, no concrete is there. So entire force, entire shear which is acting there is due to this unbalanced force dt. So if we want to make our section safe in shear, then our section must be capable of resisting this dt. So due to this dt, what all are the stresses which is going to be induced on my section? Okay, so if I am going to calculate that, so what I am going to get here? So if this is dx, we know this is b, this is b, this is dx, and here you are going to get, you can say, how much force? If this is the t, it is t plus dt. So here you are going to get an unbalanced force dt, so which is actually responsible for shear. And if you are calculating the shear stress, so that shear stress is this shear force upon area. So what is the area here? What is the area here? I know you all know from strength of material that these complementary, these stresses are same. These stresses are same in order to maintain the moment equilibrium of the section. So don't think that shear stress we have to calculate on this phase. We can also calculate on this phase because these are two mutually perpendicular axes and they have to be equal and opposite. So if one is having the tendency to go in the clockwise direction, then another is having the tendency to go in the anti-clockwise direction in order to maintain the net equilibrium of the elemental portion which you have considered. So tau is the dt upon area. So what is area here? Area is b into dx, and we know that dt, just now we have seen what is dt. Dt is dm over jd. So if dt is dm over jd into b dx, and I know that you all know that dm over dx is nothing but the shear force. I know this chapter requires the application of strength of material very much. Okay, not only this chapter but in fact earlier chapter as well, your flexor and all, those also required strength of material. So usually such topics are taught after strength of material, and I know that your strength of material in crash courses it have been covered. So in English also it is going to be covered very soon. So here dm over dx is a v and it is bjd, it is bjd. So dear friends, tau is equal to v over bjd. It means if we are going to calculate the shear stress anywhere between neutral axis and the CG of the tensile reinforcement, then maybe it is here, here, here. So this is v upon bjd. It is v upon bjd. I hope you are getting it. Okay. So actual stress profile in RCC beam is increasing linearly till neutral axis, and after that it is becoming constant, and that constant value is also known as the maximum value, and it is equal to v over bjd. Okay, isn't it? Okay, my dear. Now one more thing, this is the actual shear stress profile. If I want to make it average as IS code did, that what they considered, instead of this complex distribution, they have simply idealized their system as a constant system. Okay, so what IS code has suggested, that instead of going parabolic and then rectangular, so better we are considering a constant shear stress, and that constant shear stress is also known as average shear stress, or it is also known as nominal shear stress. It is also known as nominal shear stress. Okay, it is also known as, so the one which I have drawn with yellow color is known as nominal shear stress or average shear stress. This average shear stress is effective in effective cross section. So whenever we are going to take average here, so we will be denoting it with tau Vu, and this is Vu over Bd. So that is the reason why this yellow line I have drawn just left to this red line, because Vu over Bjd, let me take them on the same phase. If I am using these notations, then this is tau V. Okay, this is tau V, it is V over Bd. Okay, so this V and this V are same. This is Bjd. J is the factor which is less than 1. It may be it is D minus, you can say XA by 3 in case of WSM, or it is D minus 0.42 of XU in case of your LSM. So anyway, this factor is going to be less than 1. So if J is the quantity which is less than 1 and you are going to remove it, so your section would be shifting towards less, because you are going to get the lesser value. Okay, so don't be confused that you are removing J from the numerator and still the value is coming towards the left hand side. It normally it looks like it is going to the right hand side, but my dear friends, the value of J is less than 1 here. Okay, so the one which I have drawn with yellow is the nominal shear stress, or you can say the average shear stress, and the one which we have drawn, which was already drawn there with the red, it is the actual shear stress of the in your RCC beam. Are you getting it or not? Tell me. Okay. Now the next thing is that how shear is going to affect your cross section. What all are the effect of cross section? So friends, again I would say that direction of cracks or shear is going to affect your cross section in terms of cracks. So if I am considering a simply supported beam with UDL, then shear forces are maximum at the ends. So this here where shear force is maximum, so here direction of cracks would be like this. It would be like this. Okay, it is at an angle of 45 degree. It is an angle of 45 degree. Okay, as you are approaching towards center, so this crack is are not due to shear. Now these cracks are due to flexure, and due to flexure these cracks are almost vertical, and anywhere between the end and center of the support, center of the beam and support, if we are going to see the direction of cracks, then it might be lying between 45 degree and 90 degree. Okay, it would be like this. Okay, it would be like this. Okay, so with the help of linear elastic theory, we can quickly see this conceptually as well. Again, I would be saying that strength of material concepts or principal stresses concepts would be required here. If you are considering an element here, okay, so this element is not going to have any bending stress, because you know that bending moment at support is equal to 0 due to some load. Let's say that load is UDA. So here let's suppose bending moment is equal to 0. So if no bending moment, it means no bending stress, because bending stress originates only due to the bending moment, m upon I into y. Okay, so no bending moment. Yes, but this section is having a very high value of shear force. In fact, shear force is maximum here, and graph is parabolic like this. So I am not taking the element at extreme bottom point. I am not taking it at extreme upper point. But yes, anywhere between here, you can see this is the value of tau. This is the value of you can say tau. Okay, so this is the value of, let's suppose, tau, and no sigma here. Okay, so what is the value of principal stresses now? So principal stresses sigma 1 3 equals to sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 whole square plus tau xy. Okay, so here no sigma x, no sigma y. Here no sigma x, no sigma y. So value is simply going to be plus minus tau. So one tau would be like this, another tau would be like this. So if one tau would be like this, it would be having tensile nature here. It would be having tensile nature here, and it is going to break your tear your section like this. So this is the reason why angle here is 45 degree. Angle also you can justify mathematically. What about angle? So angle you can see that here tan 2 theta is equal to it is 2 tau xy upon sigma x minus sigma y, and you can see that numerator is non-zero whereas denominator is 0. So 2 theta would be tan inverse of something upon 0 is infinity. Okay, something upon 0 is infinity, so it is tan inverse of infinity, and it is your pi by 2. Tan inverse infinity is pi by 2, so theta is going to be pi by 4, or you can say in degree it is 45 degree. Okay, isn't it? Similarly, when you are taking the section at the center where the bending moment is most critical, where and shear force is not existing, so this point is going to have the highest bending stress. Only this normal stresses would be coming, no tau would be coming, and only this sigma plus 0 by 2 plus minus sigma by 2. Okay, so one value would be sigma by 2 plus sigma by 2, and another value would be sigma by 2 minus sigma by 2. So the principal stresses are the same. You also know that principal stresses contain the plane of principal stresses contain no shear force. So same thing. So the value is going to be plus sigma and minus plus sigma and 0, and that is also quite clear, plus sigma and 0. So it is going to tear, it is going to extend like this. So tearing would be vertical. Mathematically also, if you want to justify the angle this 90 degree, then what you can do, tan 2 theta is 2 tau xy upon sigma x minus sigma y. So this is going to be 0. Theta is also going to be 0. So these all are the direction of principal stresses. Here as well, 45 degree and 135 are the direction of principal stresses. So very easily you can think of the direction of cracks. Okay. So the point is, due to shear, cracks are originated in my RCC beam. In fact, in any kind of beam. Okay. So our task is to resist this crack so that our structure can be safe in shear, isn't it? So this is the theory of cracks. Okay. Now, it's whatever we have seen, all these are the consequences of the shear. Due to shear, nominal shear stress is occurring, actual shear stress profile we are seeing cracks are also developing. Now it's time to fight. Now we would be seeing what concrete can resist in shear, and if it is able to resist the nominal shear, then it is okay, and if it is not able to resist the nominal shear, then what could be the possible solutions. Okay, this is also known as the design portion of shear. Okay, are you getting it or not? Tell me, my dear friends. So first of all, let me start with the IS code provisions of shear. So there are three types of terms with which you are usually going to see the things. Okay, one is nominal shear stress, tau VU. We have seen it already. It is also known as average shear stress, also known as average shear stress. This is also, you can say, it is action. It is action. Okay. Shear strength of concrete and shear strength of concrete with reinforcement. These are the strength. These are the strength. Or you can say somewhat they are reaction. They are reaction. So very simple theory. If we want to be safe, then our action should be less than our strength, our reaction. Okay. But the thing is, in this scenario, we are having two strengths, we are having two reactions. What are they? What are they? Normally, if we want to know whether we are safe or not, then we are directly comparing the action versus reaction. But here the reactions are two, shear strength of concrete and shear strength of concrete with reinforcement. So first of all, we have to see that. Shear strength of concrete is also known as that level beyond which shear reinforcement is needed, beyond which precautions for shear is needed. If your action is lying within tau c value, then you do not need the shear reinforcement. If your action is what? Tau vu. If the developed value of shear stress is less than the strength of concrete, okay, shear strength of the concrete, in that case shear reinforcement is not that critical. If you want to provide by your own wish, you can provide with some minimum clauses available in the IS code. My dear friends, if tau vu is greater than tau c max, it means you cannot design this action for shear. The upper limit of strength is tau c max. So if anyhow your tau vu value, your action exceeds the upper limit of strength, it means no need to design this action, it is going to be failed. Okay, design or precautions are possible if your value of nominal shear stress is going to lie between tau c and tau c max. It's just like you can resemble it any day-to-day life, medical life, that if you are going for some particular blood test sample, okay, so the results of blood test sample may be characterized into three phases. One, lower limit, another upper limit. If your test results are within the lower limit, then no problem. Doctor will say that take the vitamins and calcium. That's all. You would be all right, just like your minimum reinforcement. If your test results going to lie between this minimum and maximum value, this lower and upper value, then in that case you would be given a proper treatment. Okay, and if that value is greater than the upper limit, then the situation is very critical, just like beam here. So maybe some extreme steps you have to take. Okay, and but in shear strength we are not going to design that particular problem. We are going to revise our section. Okay, because we know that nominal shear stress is V over BD. We cannot say to our client that reduce the value of shear force. We cannot design with a particular thing for a particular force. Then what alternatives we do have? We either have to increase our width or we have to increase the depth of the section. Are you getting it or not? Tell me, my dear friends. Isn't it? Okay. So the conclusion is, if tau v is less than tau c, then no need of shear reinforcement, but still if you want to provide, you can provide. If tau vu is going to lie between tau c and tau c max, in that case you have to design your shear, your reinforcement, shear stirrups. And if tau vu is greater than tau c max, in that case, my dear friends, you need to revise your section. And what is tau c and tau c max? Tau c is the lower limit of the strength and tau c max is the upper limit of strength. Now many of you might be thinking that what is this lower and upper limit? On what basis the lower and upper have been decided? In this case, shear strength of the concrete, that is tau c, is the shear strength of the concrete without any supplements, without any, you can say, medicines, without any shear reinforcement. This tau c is taking the help of grade of concrete as well as the percentage of tensile reinforcement. So based on the percentage of tensile reinforcement and grade of concrete, the value of tau c have been characterized. Okay, it is given in the table number 19 of the IS code. And shear strength of concrete with reinforcement, you might be thinking that it can be any value. Why we have restriction here? Because whenever you are going to provide a dedicated reinforcement for your shear, then why we are having the upper value? So again, I would like to say, my dear friend, this upper value is not due to tensile strength of the concrete, because it is already 0, and whatever is the tensile strength is, that we are going to make them accommodate with the help of shear stirrups, shear reinforcement. But I have shown you one this cracked one. So there is one phase which is extending. There is one phase which is compressing. So that upper limit of tau C max, that tau C max value have been designed based on the crushing strength of concrete in along its diagonal. It is defined as the crushing strength of the concrete. No doubt you can increase the shear strength in tension by providing more and more amount of stirrups, by providing thicker stirrups or anything, okay, by taking the help from a bent up bar. But my dear friends, concrete is also compelled to have some amount, it is also compelled to resist some amount of force in diagonal compression. So the upper limit shear strength of concrete with reinforcement is decided based on the diagonal crushing strength of concrete. Okay, so you can see that shear strength of concrete is that strength of concrete without shear reinforcement, and its value depends upon grade of concrete and percentage of tensile reinforcement. So this value is given to you in table number 19. As you can see that this is grade of concrete and this is percentage of tensile reinforcement. Okay. Similarly, tau C max value is the shear strength of concrete with shear reinforcement, and its values depends upon only on the grade of concrete, because the diagonal crushing strength of concrete has only to do with the grade of concrete only. Obviously, if we are increasing the grade of concrete, this value is also increasing. Okay, I have directly pasted here the snapshot of IS code just to make you a good realization. Okay, okay, my dear friends, and now we will be seeing that how we can approach towards our design. So in design approaches, we have three cases, and one is tau B is less than tau C, another tau BU is lying between tau C max and tau C, and third case is when tau BU is greater than upper limit, it is tau C max. So here you cannot design your section for shear, you cannot provide shear reinforcement because section needs revision. Section needs revision. Okay. Yes. Section needs revision. In this case, design is not that much required, but still we can proceed with minimum amount of steel. We can proceed with minimum amount of steel. So minimum reinforcement required. Okay, but yes, friends, in this particular case, when tau VU is going to lie between tau C and tau C max, so this design can be done in three ways. One is vertical stirrups. Second is inclined stirrups. And third one is bent up bars. We have 2-3 alternatives, but let me tell you one thing, that bent up bars are not to be used alone. They always have to accompany either vertical stirrups or inclined stirrups, isn't it? Okay. So first case, when tau VU is less than tau C, in that case, as I already told you, that only minimum reinforcement is required. Okay, when tau V is less than tau C, when nominal shear stress or average shear stress is less than the shear strength of the concrete without reinforcement, in that case you only need to give the minimum amount of reinforcement. So here ASV upon BSV is greater than equal to 0.4 upon 0.87 Fy, or you can say the spacing of the stirrups should be less than 0.87 Fy ASV divided by 0.43. Now, many of you might be thinking that what is this ASV? ASV is the area of steel in vertical stirrups. It is the area of steel in vertical stirrups. Okay. SV is the spacing of the stirrups and B is the width of the beam, and from starting only we are considering this representing this width as capital B, and Fy is the characteristic strength of the steel. Okay. For example, if we are using Fe 415, then we are using 415 in place of Fy. Now, what is this ASV? My dear friend, this ASV is the area of shear for stirrups. Okay. AS, area of steel, and V stands for shear force. So, area of steel required for stirrups. Most of the time, or unlike in flexor and torsion, you can say that in shear, the main role of design is due to spacing. ASV is fixed. ASV is fixed. Okay, first of all, let me tell you what is this ASV. ASV is, you can see, this I have taken from internet. Okay, this photo I have taken from internet, and you can see that this is the stirrups. Okay, and this is the main reinforcement in compressive side. This is the main reinforcement on tension side. So these are our stirrups. These are our stirrups. Okay, and they are our main reinforcement. They are our main reinforcement, main tension reinforcement, you can say. Okay, and they are main compression reinforcement. Sometimes they are from design point of view, and sometimes they only act as the hanger bars just to tie your shear stirrups. So main compression reinforcement, isn't it? In this particular case, the stirrups, you can see it is going to have two legs. These two vertical flex are going to resist your shear force. Okay, so this is known as two-legged vertical stirrups. And for example, if diameter of this vertical leg is 8 mm, so I would call it is two-legged 8 mm vertical stirrup. Okay, so for this particular case, if I want to calculate the value of ASV, then it is two-legged, because the two transverse legs are going to resist your shear into area pi by 4 into pi square. And generally 2 8 mm stirrups is having a very easy area to remember. It is 100.53 mm square. And in our case as well, most of the time, in fact 90% of the time, believe me, this 8 mm stirrups is going to work for us. Okay. If you think that the spacing of 8 mm stirrups is very less, in that case you can go for 8 mm or 10 mm diameter, like that. If you think the spacing of 8 mm stirrups is very high, in that case go for 6 mm stirrups, like that. Okay. So ASV is what? It is the area of stirrups of single vertical stirrups. If it is having 2 legs, then 2 into pi by 4 into pi square. If it is having 4 legs, then 4 into pi by 4 into pi square. Okay. So this is your ASV. Okay. This is your ASV. So just remember, it is area of single vertical stirrups. It may be having 2 legs, 4 legs, whatever. Okay. So if tau b is less than tau c, in that case we need minimum shear reinforcement, and that minimum shear reinforcement we are going to give as per this clause, isn't it? Okay. Now next is how to go for case when shear reinforcement is required. So shear reinforcement will be required for case number 2, when my nominal shear stress value is going to lie between tau c and tau c max. Only this case we have to actually design, because another case we need revision. Okay. So shear reinforcement we are going to provide in 3 ways. One is vertical stirrups, another is inclined shear stirrups, and third one is bent up bar. So in vertical stirrups, what I have done, I have assembled all the clauses at single space. So here you can see, for vertical stirrups, you can find the spacing of the reinforcement by using these 4 clauses. Okay, SP is less than equal to 0.87 Fy, ASB upon 0.4B. Okay, ASB, you know, it is the area of vertical stirrups. Okay, if it is a 2 lakh 8 mm diameter stirrups, then ASB is going to be 100.53. Fy is the grade of steel. B is the overall width of the rectangular beam. Okay, so second one, this is, you can say, from minimum reinforcement criteria. This is for minimum reinforcement criteria. Second one is design criteria, where VSU value is going to come into the picture. What is VSU? VSU is that amount of shear force for which you actually need to provide stirrups, shear force spacings. Okay, shear force reinforcement. Are you getting it or not? So VSU is that amount of shear force for which you need the shear reinforcement, isn't it? So how you are going to calculate VSU? VSU is total shear force minus tau C into B into D. Tau C BD is the minimum amount of strength of concrete in shear, and VU is the actual shear force acting on your system. Okay, so for VSU we are going to determine the spacing, and third and fourth clauses are 0.5D and 300 mm. It is as per again IS code. My dear friend, like we have here vertical stirrups, similar clauses are also available for inclined stirrups. So you can see in case of inclined stirrups, you can calculate the spacing here. Only this difference is coming here, sin alpha plus cos alpha, where alpha is the angle of inclination of the inclined stirrups, and second difference lie here. Instead of 0.75D, it is D only. My dear friends, I have recommendations for you, suggestions for you. Whenever you do have options of designing stirrups, shear stirrups, always prefer vertical stirrups. It is not only easy in terms of calculation, but also on site as well. When you have to provide vertical stirrups, still it is easy for the, you can say, engineers there to set the vertical stirrups. Okay, so third option which we are going to get here is the bent up bar. Bent up bar, actually they are not the dedicated shear reinforcement. Bent up bars are your primarily reinforcement only, especially in tension zone, which you are going to bend near the support, where the value of shear force is critical but bending is less. So basically primarily reinforcement you guys are going to define for bending moment, and bending moment is not that high near the support. So part time you can take the advantage of main reinforcement into shear reinforcement. Okay, so bent up bar we are going to bend near the support, and due to their inclined nature they are going to help in resisting the shear cracks. But yes, there is one limitation. If you want to know how much bent up bar can contribute, it is 0.87 Fy ASB into sin alpha, where ASB is the area of bent up bar. Suppose out of 8 number of main reinforcement you have bented only 2 bars, so ASB is equal to 2 into pi by 4 into pi square, where phi is the diameter of the main reinforcement. Sin alpha is the angle of inclination of the bent up bar. Generally it is kept as 45 degree. Okay, Fy is the grade of steel of main reinforcement, and VSB is the contribution of bent up bar. But my dear friend, one important thing here. Suppose if maximum shear force which need to be designed is let's suppose 120 kilonewton, and out of those 120 kilonewton, bent up bar is saying that I can give you 80 kilonewton. Then also shear reinforcement we have to provide at least for 60 kilonewton. What I want to say, the maximum contribution of bent up bar is restricted to 50% of the design value of the VSU value. So maximum contribution is restricted to WSU by 2. Okay, so if somebody asks you what is the amount, similarly one more example, suppose VSU value is 120 kilonewton and bent up bar can give this time only, let's say 50 kilonewton. So 50 kilonewton bent up bar is going to giving you, and remaining 70 kilonewton, for remaining 70 kilonewton we have to provide the shear reinforcement. Okay, so what I have said, I have concluded here that shear reinforcement is provided at least VSU minus VSB or VSU by 2, whichever is maximum. Okay, so you can check out both the cases here. So VSU was 120, VSB if it is 80, and VSU by 2 is how much? It is 120 by 2. So it is coming out to be 40, it is coming out to be 60. So we will be providing shear reinforcement for 60 as I told you earlier. And in second case, what I told you that VSU is 120 and VSB is 50, and it is 70, it is 60. So this time I have to provide shear stress for 70 kilonewton. Okay. So if you are obeying this rule, then you will not be committing mistake in the calculation of amount of shear reinforcement required, isn't it? So my dear friend, this is all theory about shear. So quickly we can see one numerical on this. So we have to design a beam for shear only, which is subjected to a UDL of 35 kilonewton per meter, excluding self weight. Here the beam is simply supported over an effective span of 7.5. If the size of the beam is restricted to 300 mm to 600 mm, and here 600 mm is the overall depth, and effective cover is 40 mm. Now you have to design the beam for shear on. Okay. Percentage of tensile reinforcement is given to you, it is 0.6%. Why it is given? Because tau c value is going to depend upon two things. One, grade of concrete, and another of percentage of tensile reinforcement. So grades of concrete is M20 and grade of steel used is Fe415. Okay. So first of all, calculation of shear force. Calculation of shear force. So it is a simply supported beam which is subjected with a UDL, and the self weight of this UDL is not given, but yes, live load is given to you, it is 35 kilonewton. Plus, what about self weight? What about self weight here? Self weight is, density of concrete is 25 kilonewton per meter cube unit weight, and size of the beam is 0.3 into 0.6. So what it is going to come? So it is going to come 4.5, I guess. Yes. So total UDL is of the order of 39.5. But this is again, my dear friend, unfactored load. So we are studying limit state method. So in limit state method also we have to apply partial factor of safety, and that is 1.5. So after applying the partial factor of safety, what is the maximum critical shear force? Maximum critical shear force occurs near the support. It is WU L by 2, because it is a simply supported beam loaded with the UDL. So maximum shear force is going to occur at the end. So W is how much? It is 1.5 times of 39.5. L is 7.5 meter. Okay. And what about this value? I think it is coming out to be, I have already solved for you guys. It is coming out to be 222.18. 222.18 kilonewton. Isn't it? Okay. Next. What is next step now? So in next step, what we can do? We can calculate the value of nominal shear stress. Calculation of tau VU. What is tau VU? Tau VU is VU over BD. So VU is 222.18 kilonewton, and BD is 300. What about effective cover? I think that is given to you. Effective cover is 40 mm. So out of 600 mm, 40 mm is effective cover. So effective depth is going to be 560 mm. So what is this value? Tau VU value is equal to 2.8. Sorry, 1.38 Newton per mm square. Newton per mm square. Okay. So tau VU value is this. Okay. Now it's time to compare action versus reaction. So third is tau C value is how much? Tau C value is the function of grade of concrete as well as the percentage of tensile reinforcement, and percentage of tensile reinforcement is given to you. It is 0.6%. So based on this, if we are going to interpolate with the table, so what was table? This was the table. So it is going to lie between these two values. So for M20, the value of tau is going to lie between 0.48 and 0.56. So by doing linear interpolation, you can get the value of tau c. So this is coming out to be 0.528. Okay, linear interpolation 0.528. So tau VU value, nominal shear stress value, is greater than tau C. Okay, and also make sure that this tau VU value is less than tau C max. So what about tau C max? For grade of concrete, tau C max for grade of M20. So what is the value of tau C max? It is coming out to be 2.8 Newton per mm square. So you can say it is a perfect case for designing. Here the nominal shear stress is going to lie between shear strength of concrete without reinforcement and shear strength of concrete with reinforcement, isn't it? So we can design this case. Okay, so most probably I can go with the vertical stirrups or inclined stirrups. So no provisions, no information of number of bars is given, so I will skip bent up bar. So if I am providing, as I told you, always try to go for vertical stirrups. If I am providing you what? Assume two-legged, two-legged vertical stirrups. What we can do? ASB is 2 into pi by 4 into 8 square. So it is coming out to be 100.53. Okay. So if I am calculating spacing now, so spacing is minimum of these four, 300 mm, 0.75D and 0.87 Fy ASV D over VSU and 0.87 Fy ASV upon 0.4 B. Okay. So on substituting these values, only this one is a design from design point of view. What about this? It is 0.87 Fy ASB is 100.53 upon 0.4 of B is 300 mm. So it is coming out to be how much? It is coming out to be how much, dear? It is 302.47. It is 302.47. So this cannot be the answer because it is already 300 mm here. Okay, so and spacing has to be least of these four. What about 0.75 of D? 0.75 of D is also coming out to be 0.75 into 560. So it is 420. It is 420 mm. Now this actually need calculation, because VSU, how we are going to calculate? For VSU, what you can do? VSU is VU minus tau C BD, and VU we have seen it is 222.18 kilonewton, and tau C we have calculated. How much tau C is there? Tau C is 0.528. So it is 0.528 into 300 into 560. It is in Newton, so into 10 raised to the power minus 3 kilonewton. So this is the final value of VSU, and on substituting that value here, so you will be getting how much? You would be getting 152. You would be getting 152 mm. So what you can do? You can go with two-legged 8 mm stirrups which are spaced 150 mm center to center. Okay. So my dear friend, this is the complete design of shear here. Okay. So let me quickly revise you this, that total design, first of all we have calculated the shear force. So shear force we have seen, it is the maximum shear force and simply supported beam is WL by 2 and W is factored. So factored shear force is coming out to be 222.18. After that we have calculated tau VU, then tau C, then tau C max, and we have seen that tau VU value is going to lie between tau C and tau C max. So we can design it for shear. So we have adopted vertical shear, vertical stirrups. So we have assumed two-legged 8 mm vertical stirrups. 8 mm is missing, two-legged 8 mm vertical stirrups. Okay, for that area of stirrups was 100.53 and spacing we have seen. Okay, so in step number 2, the calculation of VSU was the main thing. So it is actual shear force minus, you can say it is a rebate which we are getting on shear depending upon the shear strength of concrete without reinforcement. Okay, so final spacing we will be going with 152 mm or 150 mm. We cannot increase the spacing. We can decrease it, okay, because as a civil engineer, what is my suggestion? Always try to round off the things in that side where your cost is more, so that you cannot compromise with the safety. Okay, so that's all in this session, dear, and this we have used for interpolation. This I have taken from IS code table number 19. Okay, so thanks a lot, guys. So again we will be meeting day after tomorrow with next topic, which is bond. Bye bye.